Okay, so I'd like to thank the organizers for inviting me, and also thanks to Jessica for managing to pronounce my last name. Okay, so what I will talk about is joint work with Igor and Greta Panova. Okay, so first, a little disclaimer about the talk. Just, to me, this is really a 5 a.m. talk. So just take easy any slips or mistakes that I could make. Okay, so this could be a talk where the speaker falls asleep before the audience. I hope this will not happen. Okay, this is just, hopefully it's okay. Okay, so the talk is everything about certain questions about the Littlewood-Richardson coefficients. So there are many ways to define the numbers. Let's take one of these ways. You can say that these are the structure constants in the Schur basis. So if you have S lambda is a Schur function, you have 3 partitions. The lambda, mu, nu are all partitions, and you take the product, you get these non-negative integers. So there are many things that are known about the Littlewood-Richardson coefficients. Of course, this is a very well-studied object. We have several combinatorial interpretations, the geometric interpretations, like in algebraic geometry and in representation theory. But what I will talk about in particular is in the behavior of large Littlewood-Richardson coefficients. So we will be interested. This is so far this is a little bit unclear, but it will be clear during the talk. We are interested in the bounds and asymptotic estimates for large Littlewood-Richardson coefficients. Okay, so besides the Littlewood-Richardson numbers, I also need to define dimensions. So as usual, by f lambda, we denote the dimension of irreducible representation of the symmetric group. Say take the Specht module S lambda, or alternatively you say that this is the number of standard Young tableau of shape lambda. Oh, the standard Young tableau here is an example of this. So you fill the diagram of a partition by numbers 1 through n, so that they increase in rows and columns. And in particular, there is a generalization of a binomial coefficient, the product formula, the hook length formula. You can compute it. So the hooks are given by this. This is a 5, and this is free hook, and this is free hook as well. Okay. Well, this is just the basics. Okay, so the kind of a general message, a meta message of this talk, which is a little bit vague, is that large Littlewood-Richardson numbers are kind of, in a sense, closely related to large dimensions. So what is it now? It is unclear, and sometimes it will not be even true to a certain extent. But there is a kind of close connection in between the two objects. And also the Littlewood-Richardson numbers, they're, in general, as we will see, they have many similarities with dimensions. But of course, they are very different. Okay, so this is just the general message. Okay, so now let's define the following functions. So we'll be interested in these 3 functions in particular. So the first function is a function Cnk. There is 2 parameters. So lambda is a partition of n. This we take the maximal of a Littlewood-Richardson number. Mu is a partition of k, and nu is a partition of n minus k for C lambda mu nu. So over this set, we take the largest LR number. Well, Cn is a function that is just the maximal Littlewood-Richardson number. And define the function Dn that is the largest dimension. Okay? So these 3 functions will appear a lot in the talk. Okay, so let's see a little bit of numerical data. for these functions. So the first function is kind of more well-studied object, the function dk, the maximal dimension. So I just listed few numbers, and it goes like 1, 1, 2, 3, 6, and so on. The first 11 numbers. So there is a OEIS sequence for this one. Now the second sequence, the CNK, I would like just to show you just a kind of partial instance. This is the 23rd row. So the 23rd row of this sequence, the C23K. Okay, so I just listed first few values. Okay, 1, 1, 2, 3, 6. Oh, there is of course other values. Okay, so is there any guesses about what could be the sixth number? So you say not 16? 15. Well, actually, I thought that people will say 16. Okay, so it is 16. Okay, so just intentionally, I left the rest still unknown. Okay, to check the intuition. So what could be the next number? Not 16. Okay, and it's clear. Not 16. Okay, so is it 35? Okay, so the audience seems to have a very good intuition. So the next is 20. Right, so we have 20 and the rest fills out. So there is 24, 19, 30, 35. In particular, the sequence CNK is of course symmetric with respect to the middle. So we have CNK is equal to CNN minus K. There is an obvious symmetry. However, something that is difficult to guess without the numerical data, without this numerology basically, but it becomes clear after you get the numbers, is that there is a first interval that they have a coincidence. And so, like an appetizer sort of result, the first thing that I want to show you is the following theorem. Is that yes, we actually really have a stability for this largest CNK and dk. If you take this interval n to be at least k plus 1, choose 2, then the CNK and dk will coincide. So it kind of stabilizes. And there is also monotonicity in the Littlewood-Richardson numbers in the maximal ones. So if you increase n, it will go up. And well, here the same. And basically the monotonicity is based on the following fact that there is an inequality for C lambda mu. It is less or equal than C lambda. You can add a box in the first row, and mu in the box row. And there is this inequality that holds.
I saw that number 35 appears in dk as number 7, and 35 again appears in the second row by C lambda.
Yes.
Is that a coincidence? Or?
Yeah, this is a very good question, and I thought that some people might ask. This is just a coincidence. Yeah, so there is nothing behind this. Okay, nothing special.
Does the maximum for CNK occur when k is n over 2, roughly?
Yes. Well, not exactly n over 2, but roughly, yes. And I will talk about this in more detail. And this is really the interval which we are interested in, the maximal Cn. So you see that the Cnk, if you plot it, so here is the Cnk, fix n, and let k vary. It grows kind of like this. So there is this small interval that is decay, and then it goes up, and it can kind of go like this, and then there is a symmetry. So it just reflects itself. And the maximal will appear somewhere around n over 2, so it will be somewhere here. Okay, so far this is just the first result. And a quick plan about what I will talk about is, so first I will go to the asymptotics of Dn. That is a kind of more classical question. And then I will go to more recent results about the asymptotics of Cn. Okay, so the Dn and Cn were defined on the previous slide, and some people might have already forgot what this means. Okay, So here is a help. Okay, so because these numbers will appear all the time on the slides, okay, so it's good to have them here. Okay, so let's go to the largest dimensions. So it is the asymptotics of dn. It is a quite an old question, and it was so it starts from the early computations made by Bivens and others, and Bayer-Brock from '68, by McKay and by Rosala, and it was supported by some early wrong conjectures about the actual asymptotics of this function dn. So what do we get from the Burnside identity? The sum of squares is, of course, n factorial. And from here, you immediately get that the bound for dn will be at most square root n factorial, and at least square root n factorial divided by the number of partitions. And the number of partitions, this one? No, the number of partitions is not square root 1, because the total number of summons here is just Pn. Oh yeah, there is square root. Yes, you're right. Of course. There is just okay. So the number of partitions goes sub-exponentially. Yeah, thanks. Okay, so and the early wrong conjectures about the asymptotics were like, maybe there are some gigantic partitions whose asymptotics will be like square root of n factorial divided by some polynomial of n. More precisely, it was like, what if it's n? Or maybe if it's some polynomial. Okay, which turned out to be false. And the result here is of Vershik and Kerov from 1985, is that there is the following inequality holds. So the lower bound in this inequality is actually an obvious lower bound. It is the same square root of Pn, as it was mentioned. And what is remarkable here is the upper bound. So that the rescaling is exactly of order square root n. And the upper bound was a solution to a variational problem. And the related question is that what are partitions that attain maximal dimensions? So how to describe these partitions? And to some extent, these partitions can be described. And based on this knowledge that there is a limit shape to these partitions, this upper bound can be derived. This is what was the result. And so the limit shape that we have for largest dimensions, it is, so I will refer to it as VKLS limit shape. So this is Vershik-Kerov and Logan-Shep limit shape. So there is this function. Okay, so here is what we do. I need to explain it a little bit. So we draw now partition diagrams in the so-called Russian notation. Okay, so we draw it like this. And then now there is a function. So now we rotate it and then rescale it by square root n in both directions so that it's normalized. The area becomes 1. And then there is this limit shape, the partition, which becomes a piecewise linear function. It actually has a limit of this explicit function given by this formula. And that's outside of this segment, minus 2 to 2, it is just modulo x. And so more precisely, what this limit shape means is that the following inequality holds. So if you take the maximal difference between your piecewise linear function and this function, omega of x, it will not increase this bound. This is just a definition. So this picture, more precisely, this picture does not correspond to a maximal dimension, this partition. So the one I took it from Romik's book. And this is a partition sampled from the Plancherel measure on partitions, which is proportional to the dimension square. Okay. So to this limit shape, we will refer to it as VKLS limit shape. Okay, now there is a definition that will be very important to us. The definition is the following. Suppose we have some partition of some sequence of partitions. Oh, this will be like lambda 1, which is partition of 1, lambda 2, and so on as n grows. Okay, so we'll call this partition Plancherel partitions sequence. If these dimensions that correspond to these partitions, they are always very large, so they're at least square root n factorial times e to the minus c square root of n, where c is a positive universal constant. Well, these are just gigantic dimensions. These are partitions, so we call them Plancherel. They have this limit shape. So the result of Logon, Shep, and Vershikherov is that for every Plancherel sequence, there is this VKLS limit shape. So this condition that we have with c square root of n, it can be relaxed by a little of n. So instead of square root of n, you can have square root of n log n, for example, and it is still enough to have VKLS limit shape. So it still will guarantee that the limit shape will be the same. So they will be not the largest, but will be very large partitions. And for these very large partitions, you have the limit shape, so it will be this function. Okay. So these Plancherel sequences will be used quite a lot in this talk. And the problem, of course, is also just a side remark that this problem also gave us a solution to this classical Ulam's problem on the expected length of the longest increase in subsequence in a random permutation, that it is 2 square root of n, which corresponds to the length via RSK correspondence. It is the length of the first row, which is of order 2 square root n. Okay. All right, so now we go back to the...
Oh, wait, sorry, before you go on,
yes.
is there a reason you can't fix a constant in front of root n, like in the bounds?
So here...
Well, in the theorem you had bounds on both sides which had different constants.
Yeah, this is a good question, and it is an open question. So it is a conjecture, basically, that there is a constant. So far there is a bound in between the two, but conjecturally there is a constant. Okay, so now we go to the asymptotics of C of n. Okay, so C of n is here. The maximal Littlewood-Richardson numbers. So we kind of, for a little bit, we forget about the dimensions. Okay, now what Stanley did quite recently is that he computed the asymptotics of Cn. And the asymptotics of Cn of the maximal LR number turns out to be exponential. So it is 2 to the n over 2 minus big O of square root fn. Okay, so in that sense, the Littlewood-Richardson numbers are kind of very different. They're very small with respect to these dimensions, because dimensions are square root n factorial. And these are just exponential. They're tiny. Okay, so how did Stanley do that? Okay, so he used this beautiful result by Harris Willenbrink, which is also relatively recent, is that there is an analog of Burnside identity for the Littlewood-Richardson numbers. So the analog is the following. If you take the sum of squares of Littlewood-Richardson numbers, you sum through all n and mu nu, through all lambda that are partitions of n, and then mu nu, it is a function f of n, which is the number of bicolored partitions of n. So this is a very nice result. So what is a bicolored partition? So you have a partition, the same integer partition, but now you color each part of this partition by either white or black. So there are two colors, and then this is a sequence. Okay, now because this is an explicit, some concrete sequence, you can analyze its asymptotics. Its asymptotics is not difficult to get, and from here Stanley obtained this asymptotic result for the Cn. Okay. Say it again. What's the question? I didn't get.
The asymptotics of f of n is an exponent of some constant
Well, the asymptotics of f of n is 2 to the n times constant.
But f of n doesn't exceed the number of pairs of partitions.
Well, basically it is the same as you see, because this is a number. Well, if you square it, this number should be 2 to the n, so you should get of 2 to the n. This is bicolored, so if you have at least, you see, if you have this one column partition, then there is 2 to the n ways of coloring it.
So you not only cover some, but the order of...
Yes, right. So you take this partition and you color it arbitrarily.
And you...
Yes.
They're distinct, right?
Yes. Yes, all these are distinct. This could be colored in different ways. Okay. All right. So the question of that Stanley asked a similar question is, what are partitions that attain this maximum? Now, this is of course a natural question, and so from now imagine from this identity, of course you get no information about the partitions. It's like having only Frobenius identity for the dimensions. How can you guess what is the limit shape? And for the dimensions, actually the first crucial step is the access to Hooke formula. And from the Hooke formula, you can then analyze it. But the difference for the Littlewood-Richardson number says that there is no Hooke length formula. And there is no kind of formula, nice formula for the Littlewood-Richardson number. So it is actually this approach, or the same approach kind of doesn't work. Okay. And so now what we are interested, of course, is in this question. And so what we'll use is a kind of different approach of how this can be answered to certain extents. All right, now let's. So this was Stanley's result. Now let's go to the refined asymptotics, to the function c and k. So one of these kind of neat results that we obtain for the function c and k. Okay, this is a maximal c lambda mu over mu is k. Is that it is at most there is an analog. It is at most square root of n choose k, and it's at least square root of n choose k times sub-exponential term. So in particular, if k is not very small, then this number will win. This will be the main term of asymptotic. So it is sharp asymptotically. Okay, so in fact there is a little bit more that can be said about the bounds for the Littlewood-Richardson numbers. So what we do is we prove these three inequalities, these three very basic inequalities that were kind of never stated. So the one inequality is you fix mu nu and you vary over lambda. You take the sum of squares. It is still at most n choose k. Another inequality, now you fix mu and nu. You fix lambda now, but you vary over mu is a partition of k, nu is a partition of n minus k. You take the same sum of squares. It is still at most n choose k. And now you do the sum of free. You vary all the free parameters. And now it becomes at least n choose k. And now because of this sandwich, of these sandwiches, you can get this sandwich. Okay. It is kind of immediate after this. But these are really very basic inequalities.
So where does e to the power minus d sort of comes from?
It comes from the number of partitions,
Oh.
which is always sub-exponential. Yes. Okay, now, so we come to the question of what partitions attain the largest LR numbers. Okay, so this result is a little bit technical, and there are several items to this result. So first statement is the following. So take any Plancherel sequence lambda is a partition of n. And I defined Plancherel sequence a few slides ago. And I'm pretty sure some people already forgot what Plancherel sequence means. Is it the case? Okay, so I have some help. All right. So. Okay, so here is the reminder. So the Plancherel sequence is, of course, this large dimension, and it has VKLS shape. So now imagine for every, let's take any Plancherel sequence. Now, for every Plancherel, let's fix the parameter theta from 0 to 1. So we'll do like the asymptotics of binomial coefficients, basically. Now, there exists two Plancherel sequences mu that is partition of n theta, more precisely integral part. Okay, and the partition nu that is n minus n theta, such that your Littlewood-Richardson coefficient, as a sequence of this coefficient, it will have these asymptotics, the largest asymptotics. Well, square root of n choose k times this sub-exponential term. Okay, this is one statement. Right, so any questions about the statement? Okay, now the second statement is very similar. Now you take, okay, so you take now for every Plancherel's mu nu with the same conditions. There exists Plancherel lambda with this condition. Now you swap the quantifiers. You know, they exist and for all, and the same condition holds. So the same maximal asymptotics for the Littlewood-Richardson numbers. Okay. Now there is a third part also. So what you do, you have one here, and then for all here there exists a pair here, and for all these two guys there exists here. Now the third part is for all. Now take all for all Plancherels lambda and mu. Well, take these two guys to be Plancherel sequences. Then there exists new partition sequence that is perhaps not necessarily VKLS shape, but it is well, not necessarily Plancherel, but it has VKLS shape. So it is actually kind of very large, up to this order, and this is still little of n, such that your Littlewood-Richardson coefficient will be, again, maybe not the largest one, but it will be very large. This is the statement. Okay, now so I will tell a little bit about the proof ideas. So for some statements, we use kind of basic estimates derived from the identities that relate dimensions with induced multiplicities. And so the most delicate part in this theorem is item number 3, which proceeds as follows. So we and you can imagine that this third part is related to skew dimensions. So you first need to apply these results to skew dimensions, and then for skew dimensions, you also need to get some new bounds. So there are some new bounds for the skew dimensions, and then there is also this delicate argument about this VKLS limit shape. That you see this partition, it kind of goes beyond the function, the limit shape, and you can increase, you can add a little bit of layer to this limit shape, so that it will include your partition. So the area will be increased a little bit, and you can control how dimensions change, and then this will affect these terms. So it's kind of a little bit of delicate argument here. This part. Okay, so now once you have obtained this result, you kind of don't feel very satisfied with it, because what you want to really have is, say, for all Plancherels, lambda, mu, and nu, you have these largest asymptotics for the Littlewood-Richardson. That would be the natural guess, right? Okay, but it turns out that this is not exactly the case. So what we have is that large dimensions in this direction do not necessarily imply that you have large Littlewood-Richardson numbers. So there is and the property is the following. So that the concrete statement is that for all, let's take every Plancherel sequence as mu and nu that are of sizes n over 2. And there exists partition sequence lambda that has VKLS limit shape such that C lambda mu nu will vanish, will become 0. So what does it mean is that in reality, these Littlewood-Richardson coefficients, they are kind of sensitive to mild perturbations in these partitions. These changes on the level of the limit shape are invisible. So the limit shape does not recognize these changes, but you can vanish the Littlewood-Richardson coefficient. So you can make it 0. And the result is a little bit like maybe like a cheating sort of. So you just what you do is you kind of take a partition with a very long column lambda, say of size c squared n, and then the two partitions that are Plancherels will not fit by the Littlewood-Richardson rule, by the Combinatorics, and that's what makes it 0.
It's really kind of a boundary effect.
Yes, right.
If you ignored what's happening near your boundary, then you wouldn't have such a counter.
It is the case, but what we have conjecturally, what we think, is that there are free Plancherel sequences. Say lambda is a partition of n, of course, mu and nu partitions of n over 2, that you do not have 0, it will not vanish, but it can go down. And far from these largest asymptotics. This is a conjecture. So maybe it will be still large, but not the largest one. Okay, so this was so one on one direction we have attainment of free Plancherel sequences. They attain largest LR numbers. Now, in another direction, you do not necessarily have this implication that large dimensions will lead to large LR numbers. And now there is another part. There is another direction that what if you have large Littlewood-Richardson numbers? What can you say about the dimensions? This is another direction. Okay, now let's go to this third part. So the third part is the following. So what the statement is that if you have large Littlewood-Richardson numbers, they imply that you will have relatively large dimensions. Okay, so more concretely, let's take lambda mu nu, these partitions, so that the Littlewood-Richardson coefficient will have even a little bit relaxed condition for the square root n term. Then what you can say is that f lambda will be kind of very large, and f mu f nu will also be very large. But there is this linear term that does not disappear. So you have big O of n. You really have a linear term. So in particular, you cannot say that it is, from this theorem, you cannot say that it is necessarily VKLS limit shape. And it is known that for every limit shape, the dimensions will be of these asymptotics. So there is a linear term. The linear term disappears only for the Plancherel sequence. But you still have this result that it implies large dimensions in this direction. So in particular, if you take C lambda mu nu to be the largest, then f lambda, f mu, f nu will be of this large order. Okay, now, so I will tell a little bit about the proof of this fact. It's a little technical. So one ingredient in the proof is that there is this identity for the Littlewood-Richardson numbers. So if you take the sum of fixed mu nu, you take the sum of squares over lambda. It is actually equal to this identity with 4 extra letters, alpha, beta, gamma, delta. Now, some people don't like it because there is too many letters. But you can see that it is this identity. It's actually kind of useful, because what is the main feature is that it really looks like a kind of fancy recurrence relation for the space of these numbers. And what you have here, you see on top there is a number that is partition of n, and here on top there are numbers that are partitions of n over 2. And so in this kind of recurrence relation, in quotation marks, is that you have something of n order goes to something of n over 2. And now you understand, once you have this, you can get something useful for the bounds. Okay, so the immediate inequalities that you can get from here is that the maximal over lambda will be less or equal than the product of this maximal times sub-exponential term. And then now using this identity again, iterating it many times. Now you can derive this bound that f lambda will be at least this LR number to the power of log 2n times the exponential term. So there is this inequality, and once you derive this inequality, then you can derive all these free inequalities. This is the idea. And this many letters identity is actually a byproduct of skew-Cauchy identity. So for those who are familiar with the skew-Cauchy identity, you take the usual skew-Cauchy identity for Schur functions, you Schur expand it, and then compare coefficients from both sides. You get Littlewood-Richardson numbers, and in particular it is what you get, this identity. Okay, so any questions here? Okay, now the next result is about another regime. If you fix the number of rows, if you have a Littlewood-Richardson number with few rows, then we also have bounds, the lower and the upper bounds. These are given by these functions. And this result is really a mixture of some bounds on Schur functions, and also combinatorial interpretations in terms of this Knudsen-Tau hive model. So for those who are familiar, if you have a hive model, then there is, you can analyze it by looking at some freedom inside the triangle, and you can get some lower bounds on this. And the lower bounds that you get are given by this function. So in particular, if L will be of order square root of n over log n, then the asymptotics will be e to the L square log n over 2. So this is a few rows case. Now the same question, we're kind of interested in everything about the maximal numbers in different regimes. Okay, now the next result that I also wanted to mention is there is the following inequality, the so-called log supermodularity for Littlewood-Richardson numbers. So if you take C lambda mu and now you change mu to be by mu union nu and mu intersection nu. So what is a union? You take one partition, take another, you take the max. And intersection is min. There is this inequality this is of course a very beautiful result, and it is actually a very deep result. It uses some very deep representation theory. And originally by Lam, Postnikov, and Pilavsky, it was stated as some Schur positivity result. So it was written in terms of Schur polynomials. That the difference of Schur functions gives you a Schur positive function. But what it implies, this result, is that if you take the Littlewood-Richardson numbers, that is the largest Littlewood-Richardson number, then there exists free partitions that are kind of a flag type. So there is a containment. Lambda contains nu, contains mu, such that you get this largest Littlewood-Richardson number, and this for all n. So it is kind of attained on this flag of partitions. Okay. But based on some numerical evidence, we actually think that it also works in a more general setting. So it's like that is it, as Konstantin was saying. So if you have C lambda mu that is Cn, and then it is attained at the flag, then lambda mu must be a flag. So it is lambda contains mu, or it is lambda contains mu. This is based on numerical evidence that the experiments that we did. So this result is also provides a kind of reason for the sequence C and K. So when I drew it here, the sequence C and K, and from the numerical data, it was clear that it is symmetric, but it was not unimodal. And the reason of this would be that if it would be unimodal, then the max will be exactly at 10 over 2. And it's because it's exactly at 10 over 2, and this identity, it will imply that nu will be equal to mu, which is not the case. So what you really have is that the max, it is there is n over 2, and it is kind of away from a little bit away from n over 2. And so we also pose this problem that how to bound actually, how far is it from n over 2? So is there any good bounds that can be obtained? Okay, so I'm kind of wrapping it up. So this let's go to this numerical data. If you take, say, C27, which turns out to be 11, it is actually less than well, by the inequalities that I showed you, it is less than the square root of 20 to 7, which is actually 278. And which is very large, well, sort of large with respect to 11. So from this data, it feels like this number Cn, and also the refined version Cnk, must be away from the upper bound. So and we conjecture that it is away by this again by sub-exponential terms. So there is a positive constant a, such that Cn will be less than 2 to the n over 2 times e minus this constant c square root of n. Or even you can get for the refined version of this type of inequality, say. Square root, yes, yeah, there should be square root. Oh, okay, so one more square root. Yeah, but I told you, this is 5 a.m. Now it is almost 6 a.m. Okay. So another conjecture is, of course, now this kind of more important question is that you take C lambda mu nu, that is Cn, that is maximal. Does it imply that, well, conjecturally, it implies that lambda mu nu will have VKLS limit shape? So maybe it will not necessarily be Plancherel sequence, but the limit shape conjecturally will still be there. And there is a stronger version to that. And the stronger version says the following, that there is this inequality holds for the normalized dimension and on the left-hand side, and a normalized Littlewood-Richardson number on the right-hand side. And so if you are able to prove this strong inequality for some constants, for some universal constants a and b, then this inequality implies that all the free partition sequences will be of VKLS limit shape. It can be derived from this stronger version. So instead of maybe proving this, it's better to prove this inequality. So we try to optimize the constants in our bounds or lower bounds for the f lambda, but it is still there. So it is not optimized yet. Okay, so then in general you can also ask what are Littlewood-Richardson bounds for other limit shapes. So if you have, say, lambda mu nu will be some partitions of other limit shapes. You can take not necessarily VKLS. let's say, some other functions, then what can be said about, say, upper bounds on the Littlewood-Richardson numbers? So how does it affect the limit shape itself on the numbers? So there is also more behind this story. And there are also, and something that I did not want to talk about, that there are results, similar results about the Kronecker coefficients, and some of which turn out to be simpler than for the Littlewood-Richardson numbers. And there are also some generalizations to finite groups. So C lambda mu nu are considered to be induced multiplicities, and you can do this for every finite group. And you can get some good bounds if you have a few conjugacy classes. And some of these results similarly hold for general finite groups. Okay, so that is it. Thank you.